Our sun is about 4.6 billion years old. This places it roughly halfway through its estimated 10 billion year lifespan. This bodes well for us, right? Because that means we have plenty of time left where the sun is going to be stable and providing us with heat. But what exactly is the death of a star? And even further than that, what is the whole life cycle of a star? This is Cup of Science Joe, and today that's precisely what we're here to talk about. Now, let's head inside for a bit and shed some more light on this question. Stars form in large clouds of gas and dust. These clouds are known as molecular clouds. Molecular clouds can range from 1,000 times to 10 million times the mass of the Sun, and can span as much as hundreds of light years. These clouds are cold, which cause the gas in them to clump. This creates high-density pockets. Some of these clumps can then collide with each other or collect more matter in other ways, and this strengthens their gravitational force. As their mass grows, and eventually, with the passage of time, gravity causes some of these clumps to collapse. When this happens, the friction caused from it results in the material heating up. And this is what leads to the development of a protostar, otherwise known as a baby star. Batches of these protostars are often called stellar clusters, and molecular clouds full of stellar clusters are often called stellar nurseries. The Carina Nebula, seen here, is one such example of this stellar nursery. Now, our Milky Way galaxy is about 13.6 billion years old. So this means that somewhere roughly 9 billion years into its life, there was a molecular cloud somewhere in our region, I imagine, of the Milky Way galaxy. And in this cloud, our sun began its formation, steadily gathering the materials needed to move itself along into the next stage of its life. Now, at first, most of a protostar's energy comes from the heat released by its initial collapse. And this goes on for quite some time. But after millions of years, the immense pressure and temperature in the protostar's core squeeze the nuclei of hydrogen atoms together to form helium, a process called nuclear fusion. This releases energy, which heats the star and prevents it from further collapsing under the force of gravity. This process was achieved by our sun too, and once this happened, it began to stably undergo the nuclear fusion of hydrogen into helium. At this point, it became known as what scientists call a main sequence star. This main sequence phase is the longest phase of both our sun and any star's life. The star's luminosity, size, and temperature will slowly change over millions or billions of years during this phase. And as I mentioned earlier, our sun is around halfway through its main sequence stage. The gas of a star provides its fuel, and its mass determines how quickly it runs through its supply of fuel. Lower mass stars burn longer, dimmer, and cooler than very massive stars. The more massive a star is, the more quickly it burns through its fuel to generate the energy needed to keep it from collapsing. Some low-mass stars will shine for trillions of years, longer than the current age of the universe. But on the other end of the spectrum, some of the most massive stars will only live for a few million years, so very hot and very quick on their lifespan. As we know, for now, this won't be our sun for quite some time, even when considering astronomical time frames. However, there will come a day when it, like all stars, do reach the end of its life. At the start of this, its core will run out of hydrogen to convert into helium. Because the energy produced by this fusion is what creates pressure in the sun to counteract gravity, the core of it will begin to collapse. But the squeezing of the core also increases its temperature and pressure, making the sun slowly puff up. Now, I want to throw in here that these stages can differ depending on the mass of the star. For the sun, however, its atmosphere will keep expanding until it becomes a giant star. Not great news for us, because at this point it will also swallow up the inner solar system. Fusion will convert helium into carbon in the core, and in time, all of the sun's outer layers will blow away, creating an expanding cloud of gas and dust called a planetary nebula. And by this point, all that remains will be its core, which is now known as a white dwarf. It is a roughly Earth-sized stellar cinder that will gradually cool over billions of years. But the higher mass stars I mentioned earlier will go even further than this. For them, the fusion continues, converting carbon into heavier elements like oxygen, neon, and magnesium, which become future fuel for the core. For the largest of stars, this chain continues until silicon fuses into iron. Now, up until this point, these fusions created enough energy to sustain the star. However, once we reach iron in the core, the story changes. This is because converting iron into heavier elements requires energy instead of releasing energy. And this end-stage process here takes just a few million years. Once the star reaches iron, its end comes in only a matter of days. The iron core collapses until forces between the nuclei slam the brakes. Then, a rebound happens. This change creates a shock wave that travels outward through the star. The result is a huge explosion called a supernova. In this case, the core survives even still, but now as an incredibly dense remnant, either a neutron star or a black hole. The material cast into the cosmos by events such as these will enrich future molecular clouds and become incorporated into the next generation of stars. While I do find it exciting that we have the ability to study and learn about these sorts of things, I'm glad that we're doing it from afar. And I am also happy that we as humans have plenty of time before our own star, the sun, reaches the end of its life. I hope you've learned something, and I implore you to step outside tonight and look towards the stars.